Hello and welcome. In this section of our tutorials, we will reinforce what we've learned about DC motors using a sample Arduino project. This project is designed to help us apply theoretical knowledge in a practical way, making it easier to understand the motor's operation and control. We'll also be coding the application using the commands we've learned so far. This will allow us to see firsthand how each command affects the motor and the overall operation, building a stronger foundation for coding. Let's briefly examine the circuit diagram. In the circuit, there are two buttons essential for controlling the speed of the motor. We also have a potentiometer, one green LED and one blue LED. Each of these components will play a key role in our project, especially the LEDs, which will provide visual feedback about the motor's speed. Additionally, we see components in the circuit that we haven't used before, such as a diode and a transistor. These elements are particularly interesting as they introduce new aspects of control and protection within the circuit. Let's first examine how our circuit works. The two buttons on the left and right will be used to control the speed of the motor. The left button will make the motor rotate at a slow speed, while the right button will make it rotate faster. When the left button is pressed, the green LED will light up to indicate the motor's speed. When we press the right button, the blue LED will light up, showing that the motor is running at a higher speed. When the buttons are not pressed, we will be able to control the motor's speed with the potentiometer, providing precise speed adjustments. This fine control is especially useful when you want the motor to run at variable speeds that are neither too fast nor too slow. When motor control is activated through the potentiometer, the blue LED will turn on. This LED acts as an indicator that the potentiometer is now in control, making it easy to differentiate from button-based control. Additionally, the brightness of the blue LED will be automatically adjusted according to the motor's speed. This unique feature allows us to visually gauge the motor's speed based on the LED's brightness. When the motor runs at high speeds, the blue light will be brighter. At lower speeds, it will be dimmer, and it will remain off when the motor is stationary. Now, let's examine the connection pins in the circuit. Pins 2 and 3 will be used to check whether the buttons are pressed. Pins 4 and 5 will respectively control the green and blue LEDs, as well as adjust the brightness of the blue LED. Pin 5, to which the blue LED is connected, is a PWM-capable pin. This is essential for modulating the LED's brightness based on the motor speed. We'll use pin 6 to control the motor speed. This will allow us to send the necessary signals to adjust the motor's RPM effectively. We connected the output of the potentiometer to the E0 analog input, allowing us to use its adjusted value to control the motor speed. This setup provides analog input that translates into speed control. Now it's time to explain the use of the components called the diode and transistor in this circuit. These elements are essential in ensuring safe and efficient motor operation. This is a broad topic in electronics, but we'll focus on the fundamental principles for this project. It's important to understand these basics to grasp how the circuit works. First, let's look at the operating principle of the diode. Diodes are crucial in managing current flow within the circuit. Diodes allow electric current to flow in only one direction. They block current flow in the opposite direction. This characteristic is essential for protecting circuits from reverse currents. Diodes are two-terminal components made from semiconductor materials. Their design enables them to direct current flow precisely. You can see both the symbol and physical appearance of the diode. Recognizing these symbols is helpful when interpreting circuit diagrams. The anode is the positive end, and the cathode is the negative end, allowing current to flow from positive to negative through the diode. In the opposite direction, the diode does not conduct current, represented by a straight line. This feature is crucial for protecting components from reverse current surges. LEDs are actually diodes as well. If you notice, the positive lead of an LED is the longer leg, and the negative lead is the shorter leg. This design ensures that LEDs only emit light when current flows in the correct direction. When we connect voltage to the longer leg and ground to the shorter leg, the LED lights up. However, if we reverse the connections, applying voltage to the short leg and ground to the long leg, the LED won't light up. This demonstrates that LEDs are essentially diodes that emit light when current flows in the correct direction. They follow the same principles as regular diodes, but also provide visual feedback. Now, let's explain why we use a diode in our motor circuit. When the power to the motor is cut off, a reverse magnetic field is generated, resulting in a reverse electric current. This phenomenon occurs because motors create their own electrical fields while operating. A current flows in the opposite direction, and if this reverse current is not controlled, it could potentially damage the circuit. We connected a 5-volt supply to the motor, and the other side is connected to ground. However, when the circuit power is cut, the motor generates a reverse current due to its magnetic field. This backflow can potentially damage the circuit components if unprotected. To prevent this reverse current from damaging the circuit, we use a diode as a protective element. When looking at the diode's connection setup, we can see the motor's leads are directly connected to the breadboard, with both leads joined by a diode. The orientation of the diode is essential here. Its direction determines which way current can flow, preventing potential damage from reverse currents. The grey marking on the diode indicates the part that blocks reverse current. This side should face the direction opposite of the expected reverse current flow. In this circuit, we can use a diode like the one in 4007 or a similar type. This specific diode is well suited for blocking the reverse currents that motors may generate. Diodes are small components, making it difficult to read their markings with the naked eye. Using a magnifying glass can help, or you can note the specifications when purchasing. Next, we'll examine the function of the transistor in the circuit. This part is quite crucial as transistors play a key role in managing current flow. DC motors can draw more current than what an Arduino board can safely supply. This current increases, especially under load, and may harm the Arduino if not controlled properly. To prevent damage, we need to control the motor using a transistor in the circuit. The transistor acts as a switch, allowing the motor to draw power from an external source. The motor should be powered by an external source rather than the Arduino itself. This setup ensures that the motor receives enough current without overloading the board. To power this project, we should connect an adapter or a 9-volt battery to the Arduino board. This added power source will help the motor run more effectively. Otherwise, the Arduino board may sustain damage. Alternatively, you can power the motor with a separate battery or an accumulator. We mentioned that we'll control the motor through the Arduino, but how will we achieve this? To achieve this control, we need a transistor. The transistor is the circuit element that facilitates the switching of the motor. It acts as a gateway to control the power supplied to the motor. We will use pin number 6 for this purpose. This pin is responsible for controlling the transistor, which in turn controls the motor. Here, we used a 1000 ohm resistor made of brown, black, and red bands to bring the voltage required for the transistor down to a lower level. Without the resistor, the transistor could be damaged due to excessive voltage. Proper current regulation is critical in electronic circuits. The middle leg of the transistor is called the base. This is where the control signal is applied to manage the transistor's operation. When we apply a voltage above a certain threshold, current flows from the collector to the emitter, and this enables the transistor to switch. The base leg, as mentioned, is used for controlling the transistor. By adjusting the voltage here, we control the motor's operation. We'll apply energy from the Arduino to the base leg, and to regulate this energy, we must connect a resistor. This ensures that the transistor operates safely. We connect the transistor's collector to the motor's ground terminal, where we don't supply voltage. This completes the connection for current regulation. There was already a diode in between, and the motor's positive and negative terminals were directly connected to the diode. We connect the other motor terminal, which is shared with the diode, to the collector. Thus, we designed the transistor to control the motor's ground line. Transistor will manage the flow of current through the motor, switching it on and off as needed. From this, we understand that PWM outputs can be used to control both the voltage and the ground line. And transistor acts as the key component in controlling the motor's power. So how will we control the motor's speed using PWM signals? This is a crucial aspect of managing motor performance. In our previous lessons, we discussed what PWM is. Let's review it briefly to understand how it helps control the motor speed. We can regulate the 5 volts voltage on the PWM outputs, and we do this by adjusting the duty cycle of the signal. Here, we have the concept of a period. The period determines how often the signal switches between high and low states, thus affecting the motor's speed. We'll provide voltages that vary between 0 and 5 volts, with different periods corresponding to different speeds for the motor. When we send a value of 0 using the analog write command, the PWM output will be 0 volt, which means the motor won't receive any voltage and will be off. If we send a value of 64, then 5 volts will be applied for a quarter of the period, and 0 volt will be applied for the remaining 3/4 of the period. The signal continues in this manner, alternating between high and low states according to the period. Here, you can see 2 green lines indicating one period. When we send a value of 64, 5 volts is applied for 25% of the period, which is 1/4 of the signal duration. For the remaining 3/4 of the period, 0 volt is applied, effectively reducing the motor's power during that time. The signal continues repeating this cycle, and as a result, we observe an average voltage of 1.25 volts at the output. Similarly, if we send a value of 127, we create a 50% duty cycle, meaning 5 volts is applied for half of the period and 0 volt for the other half. If we send a value of 191, we obtain 3.75 volts with a 75% duty cycle of 5 volts and 25% of 0 volt. Finally, when we send a value of 255 using the analog write command, the PWM output is consistently 5 volts, meaning the motor receives maximum power. In this way, we can easily control the motor's speed by adjusting the PWM duty cycle. These topics are quite advanced in electronics. However, since we're working on such a project, we need to cover basic electronics and measurement concepts, at least at a foundational level. We've reached the end of the video on circuit setup. In the next lesson, we'll go over the code writing. Have a productive session.